Yeah, so first blank here, that'd be oxygen, right? The O would stand for oxygen. Especially if you look at your laminated periodic table, when you find O, you would see it written out. Our bigger periodic table, it doesn't have the names written down, unfortunately, but the ones at your table will have the names written down. All right, what would be the second blank? Atomic number equals what? What would you think? Yeah. 8. Awesome. Atomic number equals 8. Atomic number, that's always going to be the smaller number. Or another way of saying that, and more importantly, this is the number of protons. And this will tell you the element you're working with. Okay, yeah. Next one? Yeah, sure.
Yeah. Is it 15 something?
Yes, right.
Or
Atomic.
16.
We round up. Let's round up to 16 because it'll help us figure out one of these other ones down here. Yeah, when you're doing the atomic mass, because the atomic mass is the protons plus the neutrons. To find out the number of neutrons for like a specific one of these oxygen atoms, you want to get that to the nearest whole number. I'll explain the decimals today. That's the point of average atomic mass today, is to help you understand why are there decimal points there. All right, number of protons. So then what would that be? 8. Absolutely. All right, well then what would the number of neutrons be? What do you think? Number of neutrons. Go for it. 8. Exactly. Now, so like a lot of people, and I get it, we're thinking number of neutrons is the same as number of protons. Sometimes they are, but not always. Okay? How you know this is 8 is because the atomic mass is 16. Atomic mass, we said, is protons plus neutrons. So 8 plus what would give you 16? It would be 8. Okay? All right, number of electrons, what would that be? With each. Go for it. Yeah. Oh, sorry. What do you think? Yeah. 8. Number of electrons, this will be the same as the number of protons. Okay? Now, atoms don't always have, atoms can have different numbers of protons and electrons, but we call those ions. We'll talk about ions here in a class or two, but technically, when we talk about an atom, it's always going to have the same number of protons as electrons. Okay? All right, so that'll help you with completing that little half sheet of paper. But yeah, just a little review from last class. So then getting into average atomic mass. So this would be where you'd have your notes out. Go to you'd have a slide that says average atomic mass. That'd be the start of these notes. And again, if you lost it or something, there's extra copies in your bin. There's none in your bin. One of the other bins should have some. Anyways, to understand average atomic mass, we need to talk about something called an isotope. So here's the idea of an isotope. You can have the same element, but that same element can have different numbers of neutrons. Or another way of saying it is an isotope is an alternate form of an element. What causes that alternate form is that element having different numbers of neutrons. For example, you could have a carbon atom that has 6 neutrons. You have a carbon atom that has 7 neutrons. A carbon atom that has 8 neutrons. One that has 6 neutrons, we call that carbon 12. So the notation here is you would have the name or the element symbol, a dash, and then that number you see there, that's the mass number. Not the atomic number, not the number of protons, the mass number, protons plus neutrons. Some people confuse that with the atomic number. Now, you might ask, well, what is the difference between like carbon 12, carbon 13, carbon 14? Each of those different atoms will have different properties. Perhaps you've heard of radioactivity, like the song Radioactive, your favorite song. Isotopes are the cause of radioactivity. So what happens is When the proton and neutron number are the same or close to the same, that's when the atom is the most stable. But what happens when you start getting more, too many neutrons, you keep adding and adding neutrons, the atom will get increasingly unstable. So like carbon-12 is the most stable form of carbon. Carbon-13, a little less stable, but it's doable. Carbon-14 is radioactive. It's unstable. It'll slowly break down into a more stable form of carbon. You ever heard of carbon dating? Maybe in like a history class. So this is the basis of carbon dating. The idea of carbon dating is if you know the amount of carbon-14 that a sample should have, like whenever maybe the organism first died, or perhaps it was like a document was first written, and then you know how much you have now, you could then date how old it is by how much like the difference between those two numbers are. We'll get into some more details about how you calculate that. I believe that's going to be next class. But the point is we can use radioactivity, we can apply that to dating things. It's kind of a neat little thing that we can use.
What happens anytime after it breaks down?
We'll talk about there's some different kinds of radiation that I'll explain next class. But nuclear reactors is related to radioactivity. So when these atoms break down, they can give off a lot of energy. We could harness that energy, and power the lights and stuff. Anyways, jumping to atomic, calculating the average atomic mass. How you would do this slide's going to look really complicated. I promise you it's not as complicated as it looks up there. Here's the idea. If you want to calculate the average atomic mass of something, in other words, if you want to calculate this red number underneath your symbol, the one with the decimal points, how they calculate that, you would take the mass of one of your isotopes. Let's say this is like carbon-12, and you're going to multiply it by the relative abundance. Now, when they say relative abundance, what they're saying is the percentage as a decimal. Meaning, you'll see, we'll run through a few problems, they'll give you a mass number, and then they'll say, this is the relative abundance of that mass number. So they might say, like 72%, let's say, of the carbon-12 atoms, 72% of the carbon atoms have a mass of 12. So you do 12 times the percentage, 72%, as a decimal. What would 72% as a decimal be? Yeah. 0.72. How you get a percentage as a decimal, there's two ways. Divide by 100 or move the decimal 1, 2 spots. So why don't you add that if you're not as comfortable with that. Divide by 100 or decimal 2 spots to the left. Okay, so that's how you would take a percentage and make it a decimal. Yeah, go ahead.
How'd you get the 0.72?
So the 0.72 is, I made up 72% here, so that would be 72% as a decimal. Then let's say you have another isotope, say it's carbon-13, and they tell you the relative abundance is 28%. You would then multiply by 28% as a decimal. So what's 28% as a decimal? 0.28, right? 0.28. And how you would get that is either divide this number by 100 or decimal 2 spots to the left. So 1, 2 spots to the left. Okay? Then what you end up doing is you then add these two things together. So 12 times 0.72 plus 13 times 0.28. That answer you get there, that would be your average atomic mass. Let's get a little shaky on it. Let's do a couple practice problems and you'll see it's really not too bad. So they're telling us the element copper has 2 naturally occurring isotopes. The relative abundance and atomic masses are 69.2% for a mass of 62.93, And then for 30.8%, it's a mass of 64.93. So to find the average atomic mass, first thing you want to do is write down your masses they give you. So they give us 62.93. So let's write that down. And then they give us 64.93. So let's write that down. Then what you're going to do is multiply that mass times the percentage as a decimal. The percentage of that mass as a decimal. So they tell us 69.2. That's what goes with the 62.93. So let's multiply that by 69.2 as a decimal. What would that be? Yeah, good.
Oh, I was just gonna say 0.692.
Yeah, 0.692. You got it. Okay. Again, 2 spots to the left, or divide by 100. So then for your next mass number, multiply that by its percent abundance. So that's going to be the other percentage, the 30.8. What would 30.8 as a decimal be? Let's get the hands up. Otherwise, people just stop trying to answer. What would that be as a decimal? 30.8%. Yeah, go ahead.
0.308.
Yeah, 0.308. Okay. So then your answer would be 62.93 times 0.692 plus 64.93 times 0.308. So when you do that, you would get 63.55. 2 decimal places, that's really all you need to put your answer to. 2 decimal places is fine. As I said last class, honors chem, they worry about significant figures. We don't need to worry about significant figures in here. 2 decimal places is fine. Okay. And then AMU, remember that's the unit for average atomic mass units. That's average atomic mass units. That's your unit for mass. All right, let's do a couple more. So they're asking, what is the average atomic mass of sulfur given the following information? They got 3 percentages and 3 mass numbers for us. Okay. So what we're going to want to do is take 31.972. And you're going to multiply it by that percent abundance as a decimal. So what's 95% as a decimal? You can just say, oh, that's fine for the decimal. Wait. 0.95, yeah. Okay. 0.95. Okay. Right. 1, 2 spots. Then take the second mass number, multiply by 0.76% as a decimal. This one's a little trickier. What would that be as a decimal? Yeah. Yeah, 0.0076. 0.0076. So be careful with this. Is where I'll start seeing mistakes, is when they give you like when it's only maybe 1 digit or even no digits to the left of that decimal point. So if you go 1, that'd be 0.076 to 0.0076. All right, last mass number, 33.967. Multiply that by 4.22% as a decimal. What would it be? Yeah, it'd be 0.0422. Now then, multiply, this times that, plus this times this, plus this times this. Run the numbers, right? Run it through your calculator machine, and you get 32.06 AMU. Now, we're calculating averages here. If we were in class and I want to find the test average, how does a teacher find the test average? number of students in that class. Why I bring that up is because we're finding an average. So some sharp students might be like, well, wait a minute, why are we doing this? Why don't you just do 31.972 plus 32.971 plus 33.967, add those three together, then divide by 3. Isn't that how you find averages? Why would you not do that? It's really important you understand that to like actually understand average complex math. Otherwise you're just kind of memorizing practice problems. Why can't you just add them up, divide by 3? Let me get to you this way. What if like everybody in the class was 5 feet tall, and then one person walks in and they're 7 feet tall? Alright, so back to the original question. Why can't you just add all 3 up, divide by 3? Go for it. Ready? So here. Back to the everybody's 5 foot, one person 7 foot. What if I went to calculate the average and I did, okay, I did 5 plus 7 divide by 2. Average height in the class is 6 feet now. One 7 foot person walks in, 7 plus 5 divide by 2, average is 6 feet, right? Obviously no, but what mistake am I making? It's the same mistake you'd be making if you added those 3 numbers divided by 3. Go for it.
Because you have more, you have 95% of the atoms that have 31.97 because they're atomic number on mass.
Yeah, these are not all represented equally. I'm going to say that again. You can't just add these 3 up and divide by 3 because they're not represented equally. 95%, most of all of the atoms have this mass, and like nearly none of them have that mass. So same reason with like, you have one 7 foot tall person walking into a room where everyone's 5 foot. You can't then just have an average that's 6. That one 7 foot tall person can't swing the average that much. Just like this 32.971, its percentage is so small, it can't change the overall average that much. So that's why you're multiplying by these percentages as decimals. All right, let's keep working with this. A chemist uses a mass spectrometer to study bromine. The chemist finds 2 isotopes. One has a mass of 78.92, and another with an abundance of 50.69. And then you have a mass of 80.92 and an abundance of 49.3. Asking us then for the average atomic mass. So what you want to do is write out your masses. So we have 2 masses here, 78.92 and 80.92. So write those out. Okay? And then multiply by the percent abundance as a decimal. So the abundance that goes with 70.92 is 50.69. So what would I multiply this by? What would I multiply this by then? Yeah, but
0.5096.
yep, good. 0.5069. Okay? No. Because this should go 1, 2. So 5069. Alright, now 80.92. Multiply that by its percent abundance as a decimal. So what would that be? What would I want to multiply that by? Good. 0.4931. Yep, 0.4931. Okay. Then you want to add them up. So your answer would be 78.92 times this plus 80.92 times 0.4931. You run that through your calculator machine, and you should get 79 point, let's say 91. And then AMU, atomic mass units. Okay. Hopefully you're starting to see the rhythm with this. That's really all there is to it. They're not really going to throw you too many curveballs with it. it's really just a matter of take your mass numbers, multiply it then by the percent abundance as a decimal, and then add those all up. Give everybody a minute to finish writing. While they're doing that, take a look at that next problem. It's an interesting one. I left it last for reasons because it's kind of it's a little tricky. Maybe tricky is not the right word, but you know, it's different. All right. Last problem, an element called echerium has 3 naturally occurring isotopes. Echerium-21, Echerium-24, and Echerium-25. Now on the periodic table, echerium is reported to have an atomic mass of 23.98. So they want to know which of those 3 isotopes is the most abundant and why. What do you think? It's kind of interesting because they don't give us percentages to calculate, so it's like, well, how in the world can I even answer that then? Really think through averages.
I'll take
24, yeah, how'd you know?
because 23 is closest to 24.
Exactly. The answer is Echerium-24 because that is the closest to the average. Like, let's go back to that, like, you know, everyone in the classroom but one person is 5 feet tall. You know, one is 7 feet tall. If I were to ask you, you grab one student at random, what is their most likely height? I think we all would say 5 feet tall because there's only one out of everybody in the class that is not 5 feet tall. Similar idea here. Because we're nearly at 24, that must mean that most of the elements in this sample have a mass of 24. Or think like a test average. If it's lab safety quiz, nearly everybody got 100%. What is the score? The average is like a 98%. What is the most likely score on the quiz? 100%, right? That's super close to 100. Assuming you had 100 and like a 93. Anyways, not the best example, but hopefully you're seeing the point there. Most of them have to be closest to that average. All right, so what I want you to do is 2 things. One is, and this is kind of in order, start with the table, going over the different parts of the atom. Some of you already picked it up yesterday. I have extras at the edge of your table. And then I handed out the worksheet for you that has a few average atomic mass problems. So go ahead and work through those, and I'll be going around answering questions.